Good afternoon, everyone. I would like to introduce my report on the topic Application of Neural Network as Demodulator of SEFDM signals. SEFDM is a non-orthogonal waveform technique that provides improved spectral efficiency by packing subcarriers. The non-orthogonal signal SEFDM brings advantages such as bandwidth saving. The basic idea is to pack subcarriers closely leading to improve spectral efficiency at the cost of violating the OFDM orthogonal property. At this slide, we can see two spectrums. At the top slide, we can see OFDM spectrum. As below it, we can see a SEFDM spectrum with the bandwidth compression factor equal to 0.5. The purpose of the work is to evaluate the effectiveness of using neural networks for demodulating SEFDM signals. Tasks are represented here. On the fourth slide is represented the structure of analog of full search for the case of 4 subcarriers. The idea is as follows: implementing a neural network structure to demodulate SEFDM signals for more subcarriers is difficult due to the high computation complexity than for 4 subcarriers. Therefore, the idea was proposed to divide the subcarriers into subgroups. Each subgroup has 4 subcarriers. The input of network is fed sequentially samples of signals from subcarriers frequencies. The number of subcarriers arriving at the input of neural network can be any. The computation complexity increases slightly, thereby allowing you to use any number of subcarriers at the input without complicating the learning process. Each output neuron encodes a bit sequence that is transmitted to the subcarriers. For example, if 4 information symbol zeros are transmitted on 4 subcarriers, then the response should be on the first neuron, which is equivalent to 4 symbols 0. Now we can discuss about feedforward neural network and the training of neural network. At the left corner we can see an example of one neuron. I want to say that this structure is an example to understanding how to work feedforward. On the input of the network, samples of the signals from the subcarrier frequencies are consistently researched. The input is supplied with signal samples divided into real and imaginary components. Next, the weighting and summary are performed. The activation function calculates the output value and feeds it to the network output in this example. The learning process is named the method of the backpropagation of the error. During this process, the weight coefficients are corrected so that the error at the output of the neural network decreases. A network is considered trained if the minimum error at the network output is the same over several iterations or deviates by no more than 5%. When analyzing the bare performance, the SEFDM signal is formed at the first stage, which is superimposed with additive white Gaussian noise. And at the input of the receiver, a fast Fourier transform is performed, after which the samples are fed to the input of a neural network for demodulation and error calculation. On the left corner, we can see the result reception bare performance for the algorithm of full search of 4 subcarriers. The energy gain at alpha 0.8 and 0.9 was 3 decibel in terms of probability of error 10 to minus 3 relative to the element by element reception. At the right corner, we can see the result reception bare performance for modified full search algorithm for 8 subcarriers. As for result 0.9, we can see the energy gain is about 2 decibel, and as for result alpha equal to 0.8, we can see in terms of probability 10 to minus 3, we can see the result. The energy gain is equal to about 4 decibel. This slide shows the result of reception bare performance for modified analog full search algorithm for 32 subcarriers. In the case of alpha 0.8, there is an energy gain of 4 decibel of the bare performance curve, considering of neural network. In the case of alpha 0.9, the energy gain is about 2 decibel. Let us compare the results of the bare performance of receiving SEFDM signals in a channel with identified Gaussian noise between optimal algorithm full search is a blue curve and it is realized here. Algorithm neural network analog full search is a curve brown. The number of subcarriers is 32 and the type of modulation is BBSK. The energy gain is presented here is 1 decibel, and it is energy gain of optimal algorithm full search of a probability of error 10 to minus 3 with a compaction coefficient equal to 0.5. At the last slide, we can see the conclusions are represented here. Thank you for your attention.